Towards the end of the previous lecture, we discussed that the concept of Fourier series utilizes the complex exponential signals in its mathematical formulation. And today, in this lecture, we will establish the importance of the complex exponential signals in the context of LTI systems. And then we will see how we'll have a motivation to understand why the complex exponential signals are used in the Fourier series representation of periodic signals. Okay, but before we go into the complex exponentials part, we'll look at something related to it that we have already seen, and that is we talked about representing any discrete signal or any continuous time signal in terms of the unit impulse function. So we have here the discrete signal x of n is represented as a shifted and weighted combination of unit impulse functions, right? Similarly, the continuous time signal x of t is represented as a linear combination of shifted and weighted unit impulse functions in the continuous time. So the idea that we are going to develop now is that just as we are able to represent a discrete signal or a continuous signal as a linear combination of the unit impulse function, we can also represent any discrete signal or a continuous signal in terms as a linear combination of complex exponential signals as well. Now, using the complex exponential signal in the linear combination to represent any other signal has some important properties, which we will see later. But the whole concept of being able to represent any signal as some simple basic signals like the unit impulse or the complex exponential makes the analysis of the systems much easier and convenient. And that is why we up to now we did that representation of signals in terms of the unit impulse function, and in that process we developed the convolution sum or the convolution integral, depending on whether the system is a discrete time system or a continuous time system. Now today we are going to see how we can represent a signal in terms of complex exponential signals. But first let's see what is the importance of the complex exponential signals and what is the motivation to represent a signal as a complex in terms of complex exponential signals. So again, just to recall, the complex exponential signal has the form e power j omega naught t, and that's for the continuous time case. And if it is for the discrete time case, we will write it as e power j omega naught n, where n takes on discrete values. We'll come to that later. Now, the primary motivation in representing a signal as some linear combination of some basic signals is that we are able to construct a broad and useful class of signals using the basic signals. So just as we represented some signals using the impulse function, we now represent a broad class of signals using the complex exponential signal. And the second motivation for that is that if we are able to represent a signal as a linear combination of basic signals, then we will be able to represent the output of the system also in a very convenient and simple way by exploiting the superposition property of the LTI system. So if we know what is the output of the system for some basic signal, then the output of the system for a linear combination of those basic signals can be easily obtained in a convenient way using the superposition property. Okay, so that's the second motivation why we would want to represent a signal in terms of the complex exponential signals. Now, what is the importance of the complex exponentials? And just to recall, the complex exponential e power j omega naught t is given as cosine omega naught t plus j sine omega naught t. Now, that means it's a complex signal which has a real part given as the cosine wave, and the imaginary part is the sine wave. Okay, that's what the complex exponential represents. Now, what is the importance of the complex exponential in terms of the LTI system? In the context of this, of LTI systems, the importance is that if we give a complex exponential signal as input to an LTI system, say let's say we give e power j omega naught t as an input to an LTI system, the output is also going to be a complex exponential. So the output will be e power j omega naught t, except for some scaling factor a. So this is a constant scaling factor or an amplitude factor a. Scaling factor, okay, which is an amplitude factor. So the complex exponential, when applied to an LTI system, produces at the output another complex exponential signal, which is the same as the input complex exponential, but scaled by some factor a, and that the scaling factor is usually a complex number, but it can be a real number as well. Okay, so that's the only change. That's the importance of the complex exponential signal. So that means it makes the analysis easier because the output is having the same form as the input except for the scaling factor. So the analysis of LTI systems to signals which can be represented in terms of complex exponentials means that the output also can be represented as a linear combination of complex exponentials. And since this complex exponential is having sinusoidal components in its real and imaginary parts, what we see is that an LTI system exhibits a property called as sinusoidal fidelity. That means whatever sinusoid we apply to an LTI system, the same sinusoid comes out of the LTI system with only a change in its amplitude and or phase, okay, but the frequency of the output is the same as the frequency of the input sinusoidal signal. So that is possible when the output is the same complex exponential as the input complex exponential, because the real part of this complex exponential is a cosine and the imaginary part is a sine waveform. So together sine and cosine, or shifted versions of them, are referred to as sinusoidal signals. So sinusoidal fidelity means an LTI system does not alter the sinusoidal shape of an input signal, except in the amplitude. Okay, the frequency of the sinusoidal signal will be the same, and the output of an LTI system, when a sinusoidal is given as input, will also be another sinusoidal signal, as we have illustrated here. Okay, so if we give an input signal which is a sinusoidal waveform to an LTI system, the output is also a sinusoidal waveform, but the only change that is noticed here is that the amplitude is not the same as the input signal. The amplitude of the output is somewhere around, say, 0.7 here, but in the input signal it's 1. The peak amplitude is 1 volt, right? So there is some scaling factor on the amplitude, and you also notice that this output signal is having a slight phase shift as compared to the input signal. So you see the input signal is starting at 0 here, but now the output is shifted to the left a little bit, so it is starting at around 0.4. So what we notice is the LTI system maintains the sinusoidal shape of the waveform at the output when the input is a sinusoid. The only change that happens is the amplitude and phase. Okay, so it has the same output frequency. The output has the same frequency as the input. It has the same shape as the input, which is sinusoid, but the only difference is in the amplitude and or phase. Okay, and sometimes there may not be any phase change as well. So this we call as the sinusoidal fidelity of LTI systems. So sinusoids are components of the complex exponential. The real part is a cosine and the imaginary part is a sine. So the complex exponential signal, when applied to an LTI system, the output is also an LTI system. So there is what we call as this sinusoidal fidelity in an LTI system. Now in this context, we'll introduce a couple of important definitions. So if we apply a complex exponential e power j omega t to an LTI system, the output is also a complex exponential e power j omega t with some scaling factor, which we previously wrote as a, but now I have written it more specifically in the correct notation as h of j omega. The scaling factor is denoted as h of j omega, and that's a complex scaling factor. That means it's a complex number. Now, any signal which, when applied to an LTI system, produces the same signal as an output, of course scaled by some factor, is called as an eigenfunction of the system. So a complex exponential input produces a complex exponential output. So the complex exponential is called as the eigenfunction of the LTI system. So that's an important definition. What do we mean by an eigenfunction? An eigenfunction is any signal which, when applied to an LTI system, produces the same function at the output, which may be scaled by some factor, which we call as h of j omega. So we have this definition, which is eigenfunction of the system. Okay. Now the scaling factor that gets applied at the output, okay, that h of j omega, that scaling factor is called as the eigenvalue of the system. So the eigenvalue is the scaling factor that gets introduced at the output of the system when we apply the eigenfunction at the input. So this h of j omega that we have here, that denotes the eigenvalue, and the e power j omega t, which appears as it is here at the output, scaled by the scaling factor or scaled by the eigenvalue, we call this function as the eigenfunction. So that is our e power j omega t is our eigenfunction for this. Okay, so we have these two definitions now. What is an eigenfunction and what is the eigenvalue? The next thing that we will do is we'll check that e power j omega t, that is the complex exponential signal, is indeed the eigenfunction for the LTI system, and for that purpose we will use our the concept that we have developed earlier, where in terms of the impulse response, that the output of an LTI system is the convolution between the input signal and the impulse response of the signal. So input in this case is going to be the complex exponential, and we will take the impulse response as h of t, and we will perform the convolution of between the input and the impulse response of the LTI system, and check whether the output will be a scale version of the input signal. Okay, let's verify that. So we take our input signal x of t as our complex exponential e power j omega t, and we want to check whether this is indeed an eigenfunction. So the input-output relationship in terms of the impulse response of the system is the input convolved with the impulse response, and we utilize the commutative property of convolution, so we can change the order of this of these functions. So h of t convolved with x of t, so they are both equivalent. So we can now write that as our convolution integral. So h of t convolved with x of t is this integral h of tau x of t minus tau d tau. Now we know our x of t is e power j omega t. So x of t minus tau, so in place of t here, we are going to put t minus tau when we substitute in this integral here. So the output y of t is going to be integral from minus infinity to infinity h of tau. X of t minus tau will become e power j omega. In place of t, you put t minus tau. D tau. So we can split this as e power j omega t into e power minus j omega tau. So this integral is in terms of tau, with respect to tau. So the component which has t can be taken out of the integral. So we have taken e power j omega t outside the integral, and we have this h of tau e power minus j omega tau d tau as our scaling factor. So basically what we see is, when the input x of t is e power j omega t. The output y of t is e power j omega t multiplied by this integral term. So this integral term that we have here denotes the scaling factor, which we call as h of j omega for the continuous time systems. Okay, in the case of continuous time systems, we denote this integral as h of j omega, which is our scaling factor, and which is exactly what I had depicted here, okay, in this diagram. So that's our scaling factor, which is nothing but the eigenvalue of the system. Okay, so we see that the output y of t is the input e power j omega t scaled by this factor h of j omega. So what we have here is that this h of j omega, which is the scaling factor and is the eigenvalue of the system, it is called as the frequency response of the system. So that's the term for the scaling factor that we have in this particular case. It's called as the frequency response of the LTI system. And the frequency response is nothing but the Fourier transform of the impulse response. So h of tau is the impulse response of the LTI system. We take the Fourier transform of the impulse response to get the frequency response. So that's another important terminology. Again, what is the Fourier transform? We'll come to that later. We'll just get things started with Fourier series and then move to the Fourier transform concept. But you should remember in general that the relationship between the impulse response and the frequency response is that the frequency response can be obtained by taking the Fourier transform of the impulse response. Okay, and that is what we have specified here. And the other thing that we notice here is that the frequency response h of j omega is a continuous function of frequency. So h of j omega will have, if you plot this, it will have frequency omega, or even in terms of frequency in hertz f on the x-axis, and on the y-axis we'll have the magnitude of those frequency components. Okay, on the y-axis it will be magnitude. So what we notice is the Fourier transform produces a continuous function of frequency. Now, having shown that the complex exponential in the continuous time is indeed the eigenfunction for the LTI system, that means when the complex exponential is applied as input to an LTI system, the output is also a complex exponential, that is the same complex exponential scaled by a factor h of j omega. Now we can go on to prove the similar thing for the discrete time case as well. So we can take a discrete complex exponential x of n as e power j omega n and prove that this is an eigenfunction for an LTI system which has an impulse response h of n. Again, the general relationship between the input and output in terms of the impulse response is that y of n is x of n convolved with h of n, or by using the commutative property we can write it as h of n convolved with x of n, so which is given by the convolution sum, okay, because it's discrete time now. So that is summation h of k x of n minus k. Now in place of x of n we have to put x of n minus k. That means in place of n we replace n minus k. So we get h of k e power j omega n minus k, and this exponential can be split e power j omega n into e power minus j omega k, right? So we have split that, and since the summation is in terms of k, so the n term has no k here, so e power j omega n can be taken out of the summation, and that leaves us with the output y of n to be given as e power j omega n into this summation h of k e power minus j omega k, which we denote as h of e power j omega. Okay, now recall the distinction when we represented the scaling factor in continuous time, we wrote it as h of j omega. Okay, now the notation that we will use to write the scaling factor in the discrete time is h of e power j omega. So that's our scaling factor, which is the eigenvalue of the system, and the input signal which produces the same output scaled by some factor, that is called as the eigenfunction. So e power j omega n is the eigenfunction of the discrete LTI system, and the eigenvalue is h of e power j omega. So let me mark those things. So that's our eigenvalue, and e power j omega n is the eigenfunction. Okay, eigenfunction means it's a signal which, when applied to an LTI system, produces the same signal scaled by the eigenvalue. So that's our eigenfunction. Okay, since the input e power j omega n produce an output e power j omega n scaled by the eigenvalue, so we call this as the eigenfunction, and h of e power j omega is the eigenvalue in this particular case. So now let's summarize what are these parameters. So what we have here is h of e power j omega, which is the frequency response of the discrete time LTI system. So h of e power j omega is the frequency response of discrete time LTI system, and we obtained h of e power j omega by this calculation here, which is this summation. Okay, that denotes h of e power j omega, right? So this calculation that we are doing here to compute h of e power j omega, that is called as the discrete time Fourier transform of the impulse response h of n. So basically we are computing the DTFT, discrete time Fourier transform of the impulse response h of n. Okay, so again, what is the discrete time Fourier transform? We'll come to that later, but just remember that the relationship between the frequency response of the discrete time LTI system and its impulse response is that the frequency response is obtained by computing the discrete time Fourier transform of the impulse response. Okay, so h of e power j omega is the DTFT of h of n. And one thing you need to remember here is that the h of e power j omega that we get by computing the DTFT is a continuous function of frequency. Even though our input signal x of n is discrete, the DTFT, or the scaling factor that we get here, that is a continuous function of frequency. Okay, that's an important observation that you should remember. Okay, again, we will see all these with examples, but get familiar with the concepts and the definitions involved. So we have the scaling factor, which is the eigenvalue of the system. It's called as the frequency response of the system, and the frequency response is in general obtained by taking the Fourier transform of the impulse response. So when it's the continuous times case, we call it as the Fourier transform, but for the discrete case, we call it as a discrete time Fourier transform. In both the cases, the Fourier transform that we get is a continuous function of frequency. So what we have seen here is that the complex exponential functions e power j omega t in continuous time and e power j omega n in discrete time, they are both eigenfunctions of LTI systems, and they have the scaling factor given as h of j omega, that's for the continuous time case, and h of e power j omega for the discrete time case. So these are the scaling factors, and they represent what we call as the eigenvalues of the LTI system. And the eigenvalues are nothing but the frequency responses of the LTI system. So basically what we are trying to do is we are trying to now understand the system in the frequency domain. We are trying to translate all the information that we have from the time domain to the frequency domain so that we can get some more understanding and information about the system's behavior in the frequency domain, how the system treats or alters different frequency components and so on. Okay, so basically all this process that is going on and the mathematical analysis that we will develop later on is to convert the signals and the signal systems representation from the time domain to the frequency domain. Okay, now the importance is that as we mentioned earlier, if we are able to represent any signal x of t as a linear combination of complex exponentials. So I have taken three complex exponentials here: e power j omega 1t, e power j omega 2t, and e power j omega 3t. And x of t is constructed as a linear combination of these three complex exponentials. Now, if this is applied to an LTI system, what will be the output? Now, the idea is that, or the motivation is that, if we are able to represent a signal as a linear combination of some simpler signals like the complex exponential, then it will allow us to represent the output of the LTI system also in simple terms as a linear combination of their individual outputs by using the superposition property of LTI systems. Okay, so individually, if we apply the first term a1 e power j omega 1t to an LTI system, it will produce an output like this, which is a1 h of j omega 1 e power j omega 1t. So whatever is the input, the output is also the same thing but scaled by the factor h of j omega 1 in this case, because the input is e power j omega 1 t, right? So this h of j omega 1 is our eigenfunction, because that's the property of the eigenfunction that when applied to an LTI system, it produces the same the output is the same as the input with the scaling factor of h of j omega 1, which is called as the eigenvalue. Similarly, for e power a2 e power j omega 2t as our input to the LTI system, it produces an output given by this, where this h of j omega 2 is the eigenvalue, and for the third component here, a3 e power j omega 3t, the output is a scaled version of the input where the scaling factor is h of j omega 3. So those are the individual outputs, okay, for each of these input signals. So if our x of t is a linear combination of these complex exponentials, then the output from the superposition property will be a linear combination of these outputs, individual outputs, okay, with the same linear combination as in the input signals case, right? So that's what we will do here. So using the superposition property, we'll get our y of t as the sum of these three outputs, because the input is the sum of these three inputs now. So when we have this x of t applied as input, then the output will be given by these by this linear combination of these outputs, okay, of the individual outputs, that is. So we can represent this summation term compactly as x of t for the input signal, x of t as ak e power j omega kt, so for all values of k. So in our case, we had it as a1 e power j omega 1t plus a2 e power j omega 2t plus a3 e power j omega 3t. If you had more terms, you will have a4, a5, and so on. So correspondingly, the output will be the summation of these terms. It's a1 h of j omega 1 e power j omega 1t plus a2 h of j omega 2 e power j omega 2t plus so on and so forth for all the values of k that are relevant to the signal, okay? So what we see is that when we have the input signal represented as a linear combination of complex exponentials, we see that the output y of t is also conveniently represented as a linear combination of the output signals of the complex exponential signal itself. So the input is a linear combination of complex exponentials, and the output signal here, y of t, is also a linear combination of the complex exponentials. So that's the important property of complex exponentials, that if you are able to represent an input signal as a linear combination of complex exponentials, then we would be able to represent the output of the system also as a linear combination of the same complex exponential signals. Now we can extend the same analogy to the discrete time LTI system. So if we can represent our input signal, that is a discrete input signal x of n, as a linear combination of the discrete complex exponential, then the output is a linear combination of the complex exponential as well. So again, from the superposition property, we get this in a straightforward way, just as we did for the continuous time case. So complex exponentials, they have this important property of being eigenfunctions of LTI systems. So that means when a complex exponential is applied as an input signal to an LTI system, the output is also a complex exponential, except for a change or in its amplitude, or except for a scaling factor, the output is the same as the input signal. Now, so far, the representation of a signal as a linear combination of complex exponentials, we did not put any restriction on the values or on the relationship between omega 1 and omega 2 and omega 3 and so on, right? We chose omega 1 and omega 2 can be any other value of omega 3 can be some other value of omega. And we did not specify that there is some relationship, or what is the relationship, if at all, between omega 2 and omega 1, or between omega 3 and omega 1 and so on, okay? They can be any arbitrary values. And if we impose some condition on this, then that gives us what is called as a linear combination of harmonically related complex exponentials. And that is what we are going to see next. So that's our next topic, which is called as the linear combination of harmonically related complex exponentials, where the omega 1, omega 2, omega 3, they have some relationship between them. Okay, so we'll take the complex exponential now. We'll denote it as e power j omega 0 t. Okay, omega 0 is what we call as the fundamental frequency, and the corresponding time period is 2 pi by omega naught. We'll call it as the fundamental period. Okay, so omega naught is the fundamental frequency of this complex exponential, okay, that we are going to use. Okay, this particular complex exponential is a single frequency having omega naught. The value is omega naught, and the corresponding time period is 2 pi by omega naught, which is called as we'll call it as the fundamental period. Now, why we call it as the fundamental period and fundamental frequency? Because we are going to add more terms. Okay, we are going to take other complex exponential signals whose frequencies, which we call as omega 1 and omega 2 and omega 3 and so on, will be integer multiples of omega naught. So what we will do is, if we take another complex exponential whose frequency is twice the fundamental frequency, so we are calling omega 0 or omega naught as the fundamental frequency. If we take another complex exponential, which is e power j 2 omega naught t, so instead of j omega naught t, it is 2 omega naught, so the frequency now is 2 times the fundamental frequency. So the period will be half the fundamental period, because when frequency increases, period decreases. So when the frequency is increased by a factor of 2, the period decreases by a factor of 2. So the period, when the frequency is double, the period is half of the original value, right? Similarly, if we have another complex exponential component whose frequency is 3 times the fundamental frequency, omega naught, that's 3 omega naught, then the corresponding period of that particular component is the fundamental period divided by 3 and so on. Okay, so similarly we can have a frequency component which is 4 times omega naught, 5 times omega naught and so on. So basically, unlike in the previous example where we did not impose any relationship between omega 1, omega 2, omega 3, omega 4 and so on, here we are imposing a condition that Omega 1 is 2 times omega naught. Okay, so we can call this as omega 1 is 2 times omega naught. Omega 2, we can call this represented as omega 2, which is 3 times omega 0, and so on and so forth. And if we represent a signal x of t as a linear combination of these components of these complex exponentials whose frequencies are integer multiples of some fundamental frequency value omega naught, we call them as a linear combination of harmonically related components. So what happens is, we are basically denoting these harmonically related components as phi k of t in this case, and it's e power j omega naught t, where this omega naught is multiplied by some integer k. So when k is 0, we'll get e power 0, which is 0 frequency. 0 into omega naught is 0. When k is 1 or minus 1, when it's 1, it will be e power j 1 omega naught t, which is e power j omega naught t. And when it is 2, it will be e power j 2 omega naught t. And for 3, it is e power j 3 omega naught 3. And correspondingly, we'll have for the negative integers as well. When it's minus 1, it will be e power j into minus 1 into omega naught t, which is e power minus j omega naught t. For minus 2, it is e power minus j 2 omega naught t. For minus 3, it is e power minus j 3 omega naught t, and so on. So we have a set of these complex exponential signals where the frequency of each of the complex exponential is an integer multiple of some fundamental frequency omega naught. So k omega naught. So when k is 1, we get omega naught, which is the fundamental frequency. When k is 2, we get 2 times omega naught. When k is 3, we get 3 times omega naught. And when k is 0, we get 0 times omega naught, which represents 0 frequency. Okay, so if you are able to represent a signal x of t as a linear combination of these harmonically related complex exponentials, so we denote x of t as a summation ak e power j k omega naught t, okay, for different values of k. And of course omega naught is 2 pi by t. Okay, so we can write this as ak summation ak e power j k times, in place of omega 0 we have written 2 pi by t times small t. So this equation that we have obtained here to represent our signal x of t as a linear combination of harmonically related complex exponentials, okay, this representation is called as the Fourier series representation of x of t. Okay, so this equation is representing the Fourier series of the signal x of t. Okay, again, how to compute that, we will be seeing some examples as well shortly, and of course even in the tutorial class you will be working out a lot of examples to understand how to get the Fourier series of the signal. Okay, and one thing you need to remember here is that the Fourier series applies to periodic signals only. Okay, when we take the Fourier series, it automatically means that we are talking about periodic signals, or that means the x of t for which we have a Fourier series representation, that means x of t is a periodic signal. Only for periodic signals we get what is called as the Fourier series representation of the signal x of t. Okay. Next, what we will do is we will explore the signal x of t and see what are these components representing for each value of k. Okay, so we'll substitute different values of k here in this in this term inside the summation, and see what we get, and try to break down or look deeper into this summation term and try to interpret what is this x of t composed of, because x of t is composed of the summation of these terms. So let's look at each of those individual terms for different values of k and get a deeper understanding of what they are representing. So that's our Fourier series representation of x of t, and we are going to now substitute different values of k. So k is having values from minus infinity to plus infinity. Of course, we can't see all of them, but so let's so you have from minus infinity up to something up to plus infinity, right? So in between we have 0, and then you'll have 1 on the right, and minus 1 here, and then we'll have 2, and similarly there's a minus 2, and so on, right? So we'll have these numbers going from minus infinity to infinity. So let's look at this middle term now when k is equal to 0. Okay, when k is 0, what happens to this term? We get a0 e power j, the value of k is 0, 0 omega naught t. So e power is j into 0 into something is e power 0. So e power 0 is 1, a naught into 1 is a naught. Okay, so when k is 0, we get the term corresponding to this, which is a0, e power 0 frequency, right? So e power 0 is 1. So basically when k is 0, we get a constant term, and that is called as the DC component of the signal x of t. So the constant term is obtained for the index value k equal to 0, and that is the DC component of the signal x of t. And the DC component of the signal means it has a frequency value of 0, because it is k times omega naught, k into 0, so it's k is 0 here, so 0 into omega naught is 0. Okay, so DC component means 0 frequency component. So when k equal to 0, the corresponding frequency component, which we call as the DC component, has a frequency value equal to 0. Okay, when k equal to plus or minus 1, okay, when we put 1 or minus 1 in this term here, we will get a1 e power j, the value of k is 1, so e power j into 1 into omega naught into t, so e power j omega naught t. Similarly, for minus 1, it becomes a minus 1 e power j, k is minus 1, so we put the minus here, so j into minus 1 is minus j omega naught t. Now both these terms, okay, whether it is e power plus j omega naught t or e power minus j omega naught t, they have a frequency value of omega naught, and they are periodic signals having the same period as well. And again, that is something which we mentioned when we talked about the complex exponential signals in our previous lectures, maybe 4 or 5 lectures back, when we were discussing in detail about the complex exponential signals. We did mention that e power j omega naught t and e power minus j omega naught t are both periodic with the same period and have the same period, which is 2 pi by omega naught, right? So when k is equal to plus or minus 1, that is when it's this plus 1 or minus 1, the terms that we get here is having a frequency of omega naught. Okay, and for corresponding to plus 1, we have a1 e power j omega naught t, and corresponding to minus 1, we have e power minus j omega naught t. Okay, and these terms, when k equal to 1 or minus 1, which have a frequency exactly equal to omega naught, they are called as the fundamental components or the first harmonic component, because omega naught, if you recall, is the fundamental frequency that we chose. So the component in the signal which has a frequency equal to the fundamental frequency is called as the fundamental component of the signal or the first harmonic component. So we have this fundamental component, or it's also called as the first harmonic component of the signal. Okay, so we have two first fundamental components or two first harmonic components, which is corresponding to k equal to 1 and k equal to minus 1. Okay, next, when we have k equal to plus or minus 2, then we will get e power j 2 omega naught t, and corresponding to minus 2, it will be a minus 2 e power minus j 2 omega naught t, Again, both these components have a frequency value 2 omega naught. So you have 2 omega naught and 2 omega naught. So both have a frequency value of 2 omega naught, which is twice the fundamental frequency, and therefore they are called as the second harmonic components of the signal. Okay, the second harmonic components have a frequency value which is equal to twice the fundamental component, or twice the first harmonic component values. Okay, and in general, for k equal to plus or minus n, okay, for k equal to plus or minus 3, we will get the third harmonic components. For k equal to 4, we will get the fourth harmonic components. For k equal to plus or minus 5, we'll get the fifth harmonic components, and so on and so forth. And so in general, for k equal to plus or minus n, we will have what we call as the nth harmonic components. So for k equal to plus or minus n, we have these, we call them as the nth harmonic components. So we are just getting familiar with the terminology that we are going to come across in this topic. So we are basically, so far, we have represented our signal x of t as a linear combination of harmonically related complex exponentials. That means it's a1 e power j omega naught t plus a2 e power j2 omega naught t plus a3 e power j3 omega naught t plus and more terms to the right, and on the left we'll have a0 e power 0 plus a minus 1 e power minus j omega naught t, and so on and so forth on the left side, right? So basically what we have done here is represented our signal x of t as a linear combination of harmonically related complex exponential signals, and that is called as the Fourier series representation of the periodic signal x of t. And this equation that we have here to represent periodic signal x of t as a linear combination of harmonically related complex exponentials, this is called as the synthesis equation. Why? Because by adding these terms, we can construct x of t. That means we can synthesize x of t by adding these harmonically related complex exponential components. So if we keep adding those terms, we synthesize or generate or produce the signal x of t. So it is called as the synthesis equation, and basically that is the Fourier series representation of the signal x of t. So to summarize, what we have discussed in today's lecture is the idea of being able to represent a signal in terms of some basic signal. Previously, we had seen how we can represent a signal in terms of the unit impulse function. And today we have seen how we can represent the signals, both in the continuous time and in the discrete time, as a linear combination of complex exponential signals. And we also saw what is the motivation for this and what is the advantage or what is the importance of these complex exponentials. Okay, the advantage is that if you are able to represent the signals in terms of some basic signals like the complex exponential, then it becomes easier to analyze and represent the output of the system as well. Because we are able to represent the input signal as a linear combination of some basic simple signals. And the importance of the complex exponential signals in particular comes from the fact that the complex exponential signals are eigenfunctions of the LTI system. That means when we apply a complex exponential signal as an input signal to an LTI system, the output is also the same complex exponential signal scaled by some scaling factor, and that scaling factor is called as the eigenvalue of the system. Okay, not all signals have this property. Okay, if we give some other signal which is not the eigenfunction, the output will be a completely different signal from the input. But if that signal happens to be an eigenfunction, then we call that signal as an eigenfunction only when the output is the same as the input signal. Okay, only then we call it as an eigenfunction. Except for the scaling factor, there is no other change between the input and the output, and the scaling factor that we get is called as the eigenvalue of the system. And the eigenvalue is basically nothing but the frequency response of the LTI system, which is obtained as the Fourier transform of the impulse response of the system. Okay, so this is what we have discussed in today's lecture, and we have come across some other terms like what we call as the harmonic components, the first harmonic, second harmonic, and nth harmonics, and that arises when we lay a restriction on the representation that the frequency components are integer multiples of some fundamental frequency value, which we denote as omega naught. Okay, so we have complex exponentials which are having frequencies which are integer multiples of some fundamental frequency omega naught, and when we are representing a periodic signal in terms of such complex exponentials which are harmonically related, we call this representation as the Fourier series representation of the periodic signal, and that representation equation that we have here, it is called as the synthesis equation. Okay, we'll stop here for today, and in the next lecture we will continue with more details. We'll start from this equation, and we will also talk about some examples where we'll illustrate how adding up the frequency these individual components synthesizes the desired signal that we are interested in. So we will see how to synthesize the signal using the complex exponential harmonic components, and later on we will also see examples of how to obtain the Fourier series representation of the signal itself. So we will see it in both directions, how to go from the signal to this representation, or how to get the signal from the summation. Okay, we will see it in both directions. So to construct the signal using the summation, it's called as the synthesis of the signal. To break down the signal into these components, that will be called as the analysis equation. Okay, so we will talk about them as we go along. But for the next lecture, we are going to start with an example of some x of t, and we'll illustrate how adding up these components results in the desired signal of interest. Okay, we'll stop here and we'll continue in the next lecture.